Okay, yeah, thank you so much for invitation to Murakami-san, Jun-san for invitation. And it's my very great pleasure to give a talk at this workshop celebrating 20 years of the volume conjecture. And unfortunately, I'm too young to contribute to the initial stage of the development of volume conjecture. I was just playing around with my friends, etc. Except that there's a very interesting anecdote which I'm very tempted to tell you because Jun-san is the organizer. And when I was a grad student, I was hanging around in the bookstore and then tried to see if there's any interesting book I could actually read. And it turns out there is a very nice book by Jun-san about the knots and quantum groups. And as you know, the knot theory is very extendable to high school students and all that. So I could actually read through it. And that was very good that I could read through knots and quantum groups. But towards the very end of the book, there is a 2-page explaining, he's explaining what is the most exciting thing now, for example. And the book was published in 2000, so when the celebrated paper by Murakami about this volume conjecture is being published or so. And then that he actually wrote that the most exciting thing at the time was the volume conjecture. And since then, that volume conjecture has been in my mind for many years. Except that I was too young to do any research, but that has been in my mind, and for a while I became a researcher in somewhat slightly different field in the supersymmetric gauge theory. So a priori I wasn't really expecting any sharp connection until 5 years ago also, when I realized that there is actually a very close connection between the area of hyperbolic geometry, three manifolds, knot theory and all that, and how to quantize it, and the physics of the gauge series, or supersymmetric gauge series in 3 dimensions and 4 dimensions, etc. So it actually, you might not have, so people here mostly, I guess, mathematical aspects of hyperbolic geometry, etc., and you might not have realized it, but it's actually becoming like one field which is unified. So in view of the spirit, so before coming to any details, let me try to present a general picture of what's happening here. And so there are many different things related, but at least one ingredient, well, maybe I should start with the 3-manifold, for example. So that's because this is one of the topics of this conference. And then, well, for example, it could be hyperbolic, for example, hyperbolic structure, and it could be knot complement, and somewhat formulated more physically. This is about the study of complex Chern-Simons theory, complex Chern-Simons gauge group SL2C in general. Well, and the reasoning for that is that if you have studied the complex Chern-Simons theory, the third point equation is the flat connection, which you are all very familiar with in this context. Now, this is also very closely related with what happens in the 2-manifold. Again, the moduli space of flat connections on this 2-manifold. Well, let me call the 3-manifold M or M3, and 2-manifold to be sigma or sigma 2. And on this 2-manifold side, there is well, moduli space flat connection, which includes the Teichmüller, for example, theory in the real slice, Teichmüller space. And then this includes the moduli space of flat, including the moduli space of flat SL2R connections, which is indeed turned related to SL2C connections on this Riemann surface. And obviously there is a connection. For example, this Riemann surface might be the boundary of the 3-manifold, for example. And so that's one side of the story. And the other side of the story, we have the supersymmetric gauge theory. So this is what you might be familiar with. And there's the other side of the story. Well, since the blackboard is long, so I could try to go farther away here. And on the other side of the story, you have some supersymmetric gauge theory living in various different dimensions. And most typically, you have the 4-dimensional supersymmetric gauge theory with n equal 2 supercharges, so-called supersymmetric theory, is defined on some Riemann surface. And this theory that is defined by the data of this Riemann surface. So I might schematically write this T of delta, D of sigma, because the defining data of the theory requires the sigma. So it was a geometry here, but it's here on this side is most like defining data of the theory. And then similarly, we have three-dimensional n equal 2 theory, and defined from some three-manifold. And the relation between these two is that on this side there is a Riemann surface, which is on the boundary of the three-manifold. But here, of course, the dimension is the opposite. So what happens is that, for example, this 3D theory might be on the boundary of the 4D theory. So this is the 4D n equal 2 theory, and 3D n equal 2.
So excuse me.
Yes.
Tau of sigma, is it tangent bundle?
Oh, sorry. This is not the tangent bundle, but it's supposed to define the theory defined on sigma. In fact, right. So maybe, yeah. In fact,
Four-dimensional. What is the four-dimensional guy here?
Yeah. So it's some four-dimensional guy. But roughly speaking, whose parameter space has the modular space of complex structure of sigma, for example.
Yeah, but what is the four-dimensional space?
Oh, thank you. Okay, that's what you're asking. Right. So first of all, I could take let's first take R4, for example, R3 common 1. But let's go to Euclidean signature first. And then this on R3 first. Right. So this itself is defined in flat space. I'm going to replace that a little bit after.
But how sigma then interferes with R4?
Yeah, so in fact, this sigma, for example, that is completely different from the space-time, for example. In other words, if you have different sigma, so you could change the genus, for example. And depending on the genus, you obtain a different theory, for example. In some simple cases, you have some Lagrangian, for example, and depending on the choice of...
So sigma doesn't enter directly into the space-time.
Right. In fact, that's a very interesting point, in fact. So this is a space-time. Here, it's like a space-time, in fact, or space at least. Very geometrical. But here, it enters into the discussion somewhat abstractly of how to define the theory. And yeah, so roughly speaking, so everything comes from 6 dimensions, I'm going to say, and then it's the opposite. It's sort of like becomes extra dimensions or extra dimensions. So in some cases, you don't really see the information as a geometry, but of course, if you study everything, that information is encoded.
So you take the Cartesian product with R4 with sigma?
Yes, that's right. Yeah, that's right. Yes. So in order for this type of story to work, right, so what people usually say is that why this type of story works, because there is some 6-dimensional theory. Well, in the jargon of supersymmetric gauge series, it's called a 62-0 theory, and then compactify that. I could, for example, compactify R4 times, sigma, let's write sigma, because on this side, times 4, or 3-manifold times R3, for example. Yes. And depending on which side you compact it first, you obtain a different theory. And indeed, so for example, so that there is a correspondence between here and there. Sometimes I might call this 2D, 4D, or AGT type story. And there is a story between here and here, which I might like 3D, 3D. Although both sides are 3-dimensional, so it's a little bit confusing. So this side is 3D, and this is, so I might say 3D supersymmetric theory, and then 3D Chang-Simon, so 3-manifold side, for example. And right. So this is the type of the thing, and then right. And then what's interesting is that well, in the title of my talk, there was a word cluster algebra, for example. So that's a very precise mathematical structure. And the point is that in all these things, well, I'm not sure about this, for example, but at least everything on this blackboard, there is a cluster algebra structure. Let's see how to draw it. So maybe there is a beautiful color here. So I might use a cluster algebra structure. And these are reflected each in a different way on these ingredients. So I'm tempted to draw arrow everywhere. Sorry, I have to travel a lot to come here. So there is a cluster algebra structure underlying a lot of these ingredients. And in fact, for some consideration, cluster algebra gives a unifying viewpoint on all these ingredients. And moreover, once you understand these things in terms of the cluster algebras, and then you can now generalize the consideration to more general cluster algebras. So as I'm going to explain, some of the cluster algebra structures coming from these particular geometries is not the most general cluster algebra. And so, so these are examples of cluster algebras. And then once you understand this, you can go to more general cluster algebras and extend this story further. Right. So that's the type of the thing I want to do. Well, now since there was a question about this geometry, for example, which is a very good question, and well, I said that, for example, there is everything comes from dimensional reduction of some six-dimensional theory, but unfortunately, nobody knows. Well, there are some things are known, but very little is known about the 60 theory itself, unfortunately. So I'm pretending that there is a 60 theory, but I don't really know. But there are some understanding for this, which is that if there is a circle, and then I could compactify this to well, compactify is a jargon in this gauge theory. Like if you have S1, you can just forget about the dependence on S1. When I come to 5D theory, which is known as 5D n equal 2, but please probably don't bother too much about n equal 2. And this is a well-known gauge theory. It's gauge group so-called super Yam-Mills theory. Super Yam-Mills. And so for that purpose, I need the S1. So this theory we understand, this theory we don't understand. So we want to first come down here to understand things. So for that purpose, we want to replace this R4 by R3 times S1 or R2 times S1, so that we could first come here. And then of course this becomes R3 times S1, and this becomes R2 times S1. And right, and then this is some known theory. And then we could do various different computations. And right, so far this is just about the correspondence between theories. But if you want to extract some concrete quantities, like a quantum invariant or not invariant and things like that, you have to do some computation. This is just theories. So you want to compute some partition functions. And for that purpose, there are several different partition functions which people have thought about. But in particular, well, since this is a conference three-manifolds, I'm mostly interested in this correspondence with that. And for that purpose, the very useful quantity is obtained by replacing this R2 by S2. So this becomes also S2. So in our case, this becomes a 60 theory on three-manifold times S2 times S1. And well, except that this is well, this doesn't have to be a direct product. So it could be a direct product. It's really S2 times S1. But there could be non-trivial S fibration of S1 over S2, which is a length space. So these are some geometries. And you can consider these geometries. And it's known that there's a magical supersymmetry that the partition function defined this way, which involves the infinite dimensional path integral, reduces to finite dimensional integral, which you can evaluate, for example. So that's the type of the story which I'm coming to. And for most of my talk, I'm going to talk about S3, for example. I believe that Stavros will talk about S2 times S1, so-called 3D index, later during this conference. So I'm going to focus on mostly on the case of S3, but this is the type of the whole structure. And well, now, are there any questions so far? Yes.
So you said there are pure cluster algebra
yes.
in each
yes.
part, and you said with that algebra you can extend the story further. What
yes.
do you mean?
Yeah. So what I mean is the following. So well, at least what I mean is the following. So these geometries of the two-manifold, three-manifold correspond to some examples of cluster algebra, but the definition of the cluster algebra, as you'll see, is more general. So you can try to associate some supersymmetric gauge theory or some concrete partition function, if you like, some integral, the real quantum dialogue, etc., very concrete expression, to a sequence of cluster, modular cluster algebras. And in fact, that's more or less the, in some simple cases, that's the quantum, so-called quantum dialogism identity associated with the quiver mutations, for example. Okay, that itself, of course, is known purely mathematically. But, for example, by going through this logical supersymmetry, etc., for example, you can go to try to compute various different partition functions and obtain a different quantum dialogism identity, for example. So there are some bonuses by going through this physics, for example. Yeah, it's also useful as a way of how to think about this three-dimensional quantum field theory. So even physically, there is some interesting point. But I wouldn't emphasize that too much because this is mostly mathematical-oriented conference. Right, but but I don't know the background. So whatever question, please ask me. Yes. So, well, maybe this might be overwhelming to some people, like I don't know what 5-2 is, but please don't bother, because at least for a certain purpose of my, for the certain time, part of my talk, I won't really, well, I'll just first talk about the relation between these things, 2 manifolds and 3 manifolds, with cluster algebras, just that. And then hopefully I have some time to tell you, indicate a little bit how it's related with the physics of these things, for example, if you have time. So that's my plan. Now, so, well, okay, before proceeding, maybe I should, well, of course, what I'm going to tell you is not just by myself, and then it's based on the works of many people, in fact, including the many contributions from the audience. But at least let me acknowledge my collaborators. So, so this is from 5 years ago or so, in the chronological order. Terashima, Yuji Terashima, let's see, Kentaro Nagao, Sunjae Lee, and then Dongming, who is also giving a talk. I think he's giving a talk about the state sum model for this. Dongming Gan, Naku Ken, Mauricio Roman. So well, I learned a lot from these people, and of course a lot of other people have contributed to the subject. So let's start with this 2-manifold side of the story. Well, I could start with 3-manifold. I know that you love 3-manifold, but let's first start with the 2-manifold because at least it's simpler. Right. So at least for me, it's easier to start with the 2-manifold and then go to 3-manifold. So, so what I'm going to do, so I'm going to consider the Tahimura space or the modular space of flat connections, and I want to have the cluster algebra structure. Or this modular space is the cluster variety, for example, so-called. So that's what I want to do, what I want to explain. And then there is a nice, well, the modular space flat connection is a symplectic manifold, so there is a nice symplectic form. So in principle, at any local patch, there is a nice coordinate system, Darboux coordinate, which makes the symplectic form trivial. But of course, the question is whether we can concretely identify the coordinate. And also, we want to know the global structure of the modular space, which is to know how this coordinate transform under the coordinate transformation. Now, it's known that there's a very nice set of coordinates. Yeah, I mean, Tahimura space or the modular space of that connection has several different nice coordinates. It also, in fact, Linat also has his version of the nice coordinate. But let me tell you about the particular version due to Hock and Gonja later. And this is to start with the ideal triangulation of the Riemann surface. So I already assumed that there are sufficiently many punctures so that I could consider a triangulation. For example, if you don't have a puncture, you cannot really consider such ideal triangulation. So this is the ideal triangulation, where ideal means, well, okay, maybe people are here very familiar, but ideal just means that the vertices are the punctures. So this is the puncture surface. And then there are triangulations here and there. And then the nice statement is that there is a nice symplectic form. The Peterson form takes a very simple form. So for each edge, say I, associate the variable coordinate I, zi. Let me call it zi. And then the symplectic form takes a very simple form, qij dz over zi, which dz over dj over j, where this qij is defined by the following quiver. So if you have a triangulation like this, I draw a quiver for each triangle as follows, by arrows going clockwise, one triangle for each. And so this is an oriented graph, and this qij is the number of arrows from I to j, minus the number of arrows. So this is the number of arrows from I to j, minus the number of arrows from j to I. So by definition, it's an antisymmetric matrix, which is consistent, of course, with this wedge product.
Only yellow one.
Sorry?
Only yellow one.
Yes, only yellow one. Yes, that's right. Yes, thank you. Yes, so this yellow one is the quiver, defines the quiver. Right, so maybe give the simplest example I could think of is that suppose I have a one-puncture torus. So this is a torus, and then there's a puncture. And then I could triangulate this way, for example. And then there are three edges. Let me call it 1, 2, 3. Sorry, this is 1, sorry. And then there are arrows here and there. So 1 and 2, so there are 2 arrows. So 2 arrows, 2 arrows, total 6 arrows. So this is an example of the quiver, for example. And then that defines this antisymmetric matrix. So that is the highly non-trivial statement, and this is very useful for quantization because the symplectic form takes a very simple form. Now of course, this is just one local coordinate patch of the moduli space, but yeah, you can try to see what happens. And also we have fixed a particular ideal triangulation, which is natural. Given ideal triangulation have a set of coordinates, but of course there isn't a canonical choice, so you have to worry about the change of the ideal triangulation. And then the very nice part, I think due to Penner, is that so the change of ideal triangulation any change of ideal triangulation can be realized by a sequence of flips. Where the flip is just the operation of replacing this thing, the diagonal in one square, with diagonal in another square. So this is supposed to be part of the triangulation, so it could be there could be many edges here and there, but you just change it. And then let me log, so there are coordinates here and there, so let me call it the 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So, and then further the relation between coordinates here, let me call it the z1, z1 prime, sorry, z1, here z1 prime, etc. What is the relation between these? And that's a simple exercise in hyperbolic geometry. And it turns out that the answer is a simple one, by z1 plus z5. Z2 prime equals Z2, 1 minus Z bar 5, inverse, in fact the same for 1 and 3, and same for 2 and 4, and then 5 prime is equal to 5 inverse. Right. In fact, this is supposed to be, if it's hyperbolic, for example, it's supposed to be realized from H2. The ideal triangles are triangles like this. And if you have 4 points, there's one more point. And the two diagonals you're talking about here is this. So this actually comes from the statement that product of this and that is the same as product of this and, right, maybe I should write 1, 2, 3, 4, 5, 6, and then the product of lengths of 5 times 6 equals the product length of 1 times 3 plus 2 times 4, which is the Topology theorem, which you're very familiar with. But this is a hyperbolic space, and there are actually some issues related to regularizations, which is subtle, but that's more or less the issue. Now it turns out that this is a just simple example, one of the simplest example, the cluster algebra. So this is essentially the cluster transformation. And in fact, I almost feel that maybe if you have studied this historically, we might have discovered the cluster algebra by thinking about this, and it's very close. So in the cluster algebra case, so generalization.
Okay, do you assume positivity here or
Positivity of what?
of variables?
Okay, I see. Well, so far, well, depends on whether you want to do SL to R or whether you want to do the coordinates in complex coordinate, for example. Right. But in fact, if you restrict to the real space, I think, for example, positivity is very important, I think.
Yeah, if it is positive, then it's one global. So your space is just one chart is enough.
Yeah, so to some extent, yeah, that's right. So for example, modularized triangular space, I thought that was is sort of contractible if I correctly, right? So for example, so but the point is at least it's fine to stick with a particular triangulation, but the choice is not canonical, for example. So you have to worry about the change, in fact. And in fact, and also the fact that there is ambiguity in the choice of triangulation is actually more or less the ingredient to lift it to 3 dimensions. And
I think you also need to cut off all of your vertices.
Oh yes, exactly, yes,
like,
that's right.
it becomes infinity.
Yeah, that's right. So that's what I was mumbling, like regularization. Yeah, thank you so much. For example, so you have to regularize, for example, and then and in fact, for example, you might tempted to define this as a length, but then it depends on the ambiguity. But then if you take the cross ratio, these ambiguities cancel out, for example, and in fact that has a very nice counterpart in cluster algebra. So well, ambiguity doesn't have a great counterpart, but you have to take a cross ratio, one variable to cross ratio, and that goes by then going from plus x variable to y variable, for example. Right, so and then you could also do that type of computation. And in fact, if you're interested in, well, if you are fortunate enough to read Japanese, and if you're interested in details, it happens that I published a book about about this all these things I'm talking about. Unfortunately, it's still in Japanese, but I'm trying to translate it and put it to the archive soon. But I'm very easy, so don't expect me to do that in a month or so. Right, and then it has an exercise trying to explain this, how to regularize and the regularization cancel out and all that, right? But that's highly non-trivial point, yes. Right, so this is the generalization, and the definition of cluster algebra is a little bit clumsy, but basically the idea is to replace that quiver. So I have this quiver coming from triangulation. But maybe if we can just forget about the triangulation altogether, because once we have this, for example, I could have a set of coordinates, for example. But first of all, this index I, for example, that corresponds to the level for the vertex of the quiver. So more general Q, which is an antisymmetric matrix, and then you can try to associate the coordinates, for example, and some generalization of the coordinate transformations. And well, I won't write down the whole definitions, but for example, since it's here, the generalization of this will become something like this. So here, I'm changing, the change happens at position 5. And similarly, if the position change happens at change at the vertex k, so now ij becomes the vertex of the quiver. Here that was edge, but since I have now taken the graph, dual graph, so no, not the dual graph, but anyway, so this graph, so it becomes the level for the vertex, and then for example yj becomes yk inverse when I equals to k. And then in general, there might be more general expression, for example, minus qik plus, and then 1 plus, hope this is correct, yk, minus, sorry, this is qik, And this is a sign QIK. I think some expression like this. Let me double check. Oh, sorry. It's here. Okay, so here you don't need to have the. Right. Where this is, well, okay, I don't if I need to introduce that. So this is just the maximum of minus QIK 0. So it depends on, it might be 0 or non-zero depending on the value of the sign of QIK. So roughly speaking, if there are, for example, in this case there was just one arrow, but if there are two arrows, you have a power of 2 everywhere, for example. So that's the type of the crossed algebras. And well, a lot of the story, like for example, there is some nice two-form or Poisson structure generalized to more general crossed algebras. Now, since this is a workshop on three-manifold, let's come to three-manifolds. And in fact, since we have already explained the two-manifold story here, the lift is actually not that hard. And that will reproduce something you already know. So let's first go to three-manifold. But now I want to still take advantage of this structure. So what did we do? Well, what we do is that, well, of course, if it's a three-manifold person, you might be tempted to regard this, etc., as sorry, the other way around, as gluing this tetrahedron. Well, of course, right. But now I want to regard this three-dimensional too. So what happens? It used to be two-dimensional and this is a flip, but now I just regard it as a face of the tetrahedron. So suppose that I have the tetrahedron glued together, ideal tetrahedron glued together, and then some of the faces are glued together, so you don't see. But suppose that some of the faces are not glued, and those are the faces shown here. So it's hard to explain for me to, I'm not good at drawing pictures, but for example, this is supposed to be three-dimensional picture, and if you cut here, for example, you might see a picture like this and that, and how many? 3? Like for example, 3, for example. Oh no, one more, there should be one more. So there is ups and down, for example. And this line is supposed to be this face, along this face, and there might be some other edge, and then that corresponds to, so there in general, there are a lot of ideal tetrahedra here and there. They are glued together, but they are unglued faces. So this is one-dimensional lower, so I don't only see the edge, but they are unglued faces. And those unglued faces you see here. So that's the type of the structure. And so everything here is filled with either tetrahedron, but here it's empty. Now then what you have is the hollows. So well, it used to be that there is one parameter here, like a 1. So the counterpart now is that if there is a 1, that corresponds to this point, so the wedge. And the meaning of that parameter now is that it's the modulus for this. So namely, it's a complexation of the dihedral angle between this head and that. So that's Z1. And this is a 5 and 2, 3, 4. So here, for example, you have 5. So here it's a Z5, for example. And here it's Z3. Sorry, orientation is probably not. Sorry. Oh, okay. I'm not consistent with the orientation. And then, of course, for each tetrahedron, we have the modulus, like a Z. And then we have the Z prime and ZW prime. In the standard notation. Now, then let's just glue these things together and then see what happens. And so what happens is that, first of all, for example, for this one, you have extra, you glue this extra tetrahedron together here. So you have to multiply further by this angle, which is the Z. So Z1 is replaced by Z1 times ZW prime, and Z2 similarly replaced by, so this is same for 3 and 4. So it's the same amongst 1 and 3, prime, for example. Now, but of course there is an internal edge, for example, here. So everything is glued together there. So there is a gluing equation. Along with an internal edge.
We change the signs of sets.
Oh, sorry?
There should be sign change for sets to interpret them as the hyperbolic shapes.
Well, let's see. Well, sorry. Well, okay. Well, I was using the yeah. Okay, the cluster. There is a sign difference between cluster variable and right. So maybe I should have used the same z. So I should have used the z tilde or something like that. Thank you. Yes. Yes, that's what I'm coming to. Yes. So let me quote the z tilde, for example. Sorry. Yes. Hopefully that clarifies the. Right. So this is very purely three-dimensional consideration. And then since this is like z prime, you can correctly 1 minus z. Z double prime is 1 minus z inverse. But then, for example, z prime, oh sorry, this is supposed to be tilde. Maybe this is too much for notation. And then, but z prime is inverse z5, z5 tilde. So, it turns out that this is equal to z1 tilde, 1 minus z5, let's see, z5, right. And this is equal to z24 inverse right, inverse, right. And then z5 prime, z prime am I too fast or maybe I'm too slow? Yeah, so you agree things together. So just they use this very standard definition of z prime, etc., and they just impose the gluing equation, which is here. Otherwise, it's just that there are more faces, so you have to multiply. That's the rule here. And then so we obtain something like this. And of course, that's the same transformation of this up to sign, which Rinat was pointing out. I hope it's the same. I'm praying it's the same, but it looks the same. Yeah. so they're the same up to the parameter identification, like the I equals to at least the transformation property is the same times minus. Right. So this is how it works. So this is basically the argument. It's extremely elementary. So it's just that the familiar things, this thing, z prime, etc., which everybody here is familiar with, it's just the same as this structure. So basically for that reason, there is a precise correspondence between this thing, which is an example of the cluster algebra, with this what we find from three-manifold by gluing things together, etc. So this is one observation, and then you can try to expand upon that to see that, for example, in some cases, like for example, this is like a time evolution of the ideal triangulation. So for some geometries, like a mapping torus, where it's a Riemann surface times S1, but with in general along the S1. In those cases, you can, for example, prove by just modifying this a little bit that this so-called cluster variable, which satisfies this, solves the gluing equation, for example. Yeah, so that was my paper with Yuji Terashima and also Kentaro Nago. It's actually, I have a lot of memories with that paper because unfortunately Kentaro Nago later passed away. But anyway, so that's the type of the, so this is just how cluster algebras have anything to do with three-manifolds. So any questions? Good. And then now we have this structure, then you can try to quantize it. And the quantization is not that hard in the sense that, well, if you want to do quantize, you can try to take advantage of the symplectic manifold. So symplectic structure. So I can propose this in general, for example, okay, I could explain this or that, but for example, it used to be that there is some, so originally, classically, you have something like this, dz equals zi, which dz over dj, so that's classical. But if you want to quantize it, so this is just in particular case, a la Chekhov-Fock, for example. And in fact, the connection to cluster algebra in two-dimensional case was pointed out by Fomin, Shapiro, and Thurston, I think, in 2D case, right? So, and then you can try to replace it by a set of operators, satisfying some non-trivial commutation relation like a zi hat, zi hat equal to q to qij. Well, let's change it for my taste, and then zi for example. So set of variables. So this is index is supposed to run over the vertex of the quiver. And then they satisfy this commutation relation, where q is the quantization parameter. Q is exponential h bar, and the meaning of h bar differs from in examples, but in the case that I'm talking about, which corresponds to S3 partition function, this might be I pi b squared, if you are familiar with the Liouville notation. And right, and then interestingly, this flip, for example, flip is also quantized to be an operator. So this is a quantization. And then the flip, for example, is promoted to some operator. Let's call f, for example, f hat. So let's call this algebra AQ, for example. And then it maps one quiver to the algebra associated one quiver to another quiver. So this is after the flip. And then, so the precise form, this is basically like replacing this by hat, but you have to make sure that there are some appropriate power of the Q, which is consistent with this commutation relation. So I'm not sure there is a uniqueness. Well, some people I think have tried to prove the uniqueness, but at least if you try to find the ways, well, this becomes non-commutative, so you have to worry about the fact that the Q are popping up here and there. But if you try to find such combination such that this equation is preserved in the sense that you start with this equation for Q, and then you should obtain the computation relation for the quiver after the change. And then there isn't that much possibility, and that more or less uniquely fixes this operator. So even this thing, so these are the quantization of the coordinate, but not just the coordinate, but this change coming from the change of the ideal triangulation is also quantized.
Can we formulate this story in category theory? So that
Well, let's see. So at least first of all, it's formulated in terms of the cluster algebra, for example. But now if you want to formulate everything categorical, there's a cluster category, for example, which I don't claim to be that familiar with. But I think, yeah, it's possible, for example. And interesting, at least some, for example, the quantum diagonalism identity, which I might have time to talk about, for example, is motivated at least, well, maybe even proven from, or motivated by, maybe, but from the cluster category, for example. Although I have at least modulo some mathematical rigorousness, I have some more pedantic, more down-to-earth proof of this quantum diagonalism identity. But yes. So that's one fairly conservative answer. But to some extent, I like actually more sort of a bold answer, which is that to some extent thinking about physics behind, for example, is sort of like considering the category. It's not the categorification in the usual sense of categorifying not invariants of Markov, etc., which has a very specific meaning, for example, replacing the cohomology or Euler character by cohomology, Poincare algebra, Poincare polynomial, etc. But here I have something more, a little bit vague. But if you have some, the underlying, so this is just a very concrete algebra structure, but underlying it there is a very rich structure of supersymmetric gauge series, which includes all sorts of stuff, for example, the moduli space and the Lagrangians and everything, all that. And that's similar to categorification in the sense that once you understand that part, you can apply various different functors, for example. to go to various different the categories, for example. And then, for example, the physics way of saying that is that if you have if you identify a particular gauge theory, you can compute various observables, different partition function or different correlation function, for example. And depending on which quantity you consider, you obtain a different looking answer. And if you are concerned only about the quantum invariant, etc., it looks like that there are various different things, and then you don't really see the connection between these. But of course, there is underlying physics, so it looks like a category which unifies the whole structure. So this is the type of the story which you can talk about. And well, in fact, for example, once you have this operator, what you can do is that right. So for example, suppose given a quiver and a sequence of change or flips. Or, in fact, in the crust, so flip is applies, the name flip applies to the case of two-manifold, and in general, I didn't introduce the name, but in the crust algebra, it's called a mutation. So that's each of these represents this type, and then there will be a sequence of operators, F, where there is a choice of which, with respect to which edge you take the flip. Here I'm choosing this edge to do the flip. Similarly, there is a choice for each vertex. You can try to do the mutation. So there is an index I, J, K, and there is a product. And if there is operator, you can try to take expectation value by choosing a particular representation. So these are the standard representation. And try to take expectation value. Well, sorry, maybe this is a more physics notation. I might do that, but anyway, right. So, but anyway, so there is a sequence of operators, for example. So, given a quiver with a sequence of mutations, and then there will be a sequence of operators, and then, for example, the non-trivial statement is that suppose that if you have two sequence of mutations. Yeah, so given a quiver and a sequence of mutations and another sequence of mutations, and I obtain the same quiver first of all, but not just the quiver, but also there are some variables which I was writing yi, and these are transformed after many sequences to some set of variables. But suppose these are also the same. Assume. And then the statement is that then the sequence of product of mutations, so product of this F on the left, above, and the product of F's. Well, mutations at vertex say I1, I2. So this is J1, J2. And then these are supposed to be these are the same. And this is an abstract expression because I didn't like complete things about F. But it turns out that this F is given by nonlinear transformation plus the quantum derivation. So for example, this includes the pentagon for the quantum dialog, for example. And if you consider more general quiver mutation, in fact, people have worked out various examples, and you can generate infinitely many identities for quantum dialogrism, for example, operator identity for quantum dialogrism. Yes?
Independent?
So that's an extremely interesting question, and I don't know the answer in general. But for example, there are some things I have checked, for example. Suppose that, for example, I could start with AN quiver, for example. And there is a canonical sequence of mutations. Basically, first mutate on the odd vertices, and then even vertices, and then repeat that several times, up to dual Coxeter number plus 2 or something like that. And in that case, I have checked, for example, that it follows from pentagon. And that's,
but this is triangulation case.
Yes, that's right, that's right. Yeah, that's right. And then you can try to go to Bn, for example, Cn, etc. And I think also in that case I have checked that, well, maybe I don't have a general proof, but I have checked that. So for finite type quiver, for example, then it seems that everything follows on pentagon.
Even for exceptional?
Yeah, well, I thought that was the, well, okay, maybe I didn't check that carefully. Yes, sorry. But, well, sorry, but right, so I'm not sure if I had a proof, but I was close to proving that that's the case for finite type quiver. But I shouldn't say that I've proven it. But, yeah, and then if you go.
So this is include infinite type?
Yeah, that's right. So whether it actually, that's an extremely interesting question, whether these identities can be proven just by pentagon. And of course, if you go to the classical regime, it reduces the right. As you have, in fact, that's right. There is a very nice paper by Rinat and also Tomoki Nishi about the reduction of these Q-dialog identity to classical dialog identity. And in the classical dialog identity, it's more or less known that the pentagon is enough. But I don't know the corresponding statement for quantum. Right. So there's some discussion with Hyun-Kyu Kim, which about that topic. We worked out many examples, etc. But certainly, I don't know the general status. Yes.
So the pentagon identity does not determine the quantum dialog?
Sorry?
The pentagon identity does not determine the quantum dialog?
Well, at least not that I know of. Do you know the proof? If there's a proof, I'd love to hear it, in fact. I mean, I think that's, well, okay, they're experts in the Q dialog, so I'm actually very glad to hear about your opinion. And I kind of expect that the answer should be yes, but I just want the clear-cut proof, sorry, yes. If you have a proof, I'm glad to, or maybe it's in the literature, but yes. And that
It is not known.
Okay.
You need the difference equation. Difference equation is enough.
Mm-hmm. Right. I see. So, yeah. So, okay. But anyway, it's a very concrete question, for example. So, and it also has an interesting implication. For example, I'm going to translate. Well, I hope I have some time to say some words about it. Okay, I only have 10 minutes or so, but I'm going to translate everything in terms of supersymmetric gauge theory, for example. Then I could translate the quantum dialog identity as some dualities of supersymmetric gauge theory. So this is identity, so that's translated the statement that some theory is related to some other theory, for example. And then the question has a reformulation that are these dualities really new? And if there is a duality corresponding to the pentagon, and does that enough to recover all other known dualities, for example? And right, so that's the type of the story. Again, if you have some concrete things, I'm very happy to hear. Right. So let me comment extremely briefly about how at least I hope to explain how the cluster algebra structure arises and how to quantize it. Sorry, I didn't write down everything. Sorry, I didn't have time. But then now I try to explain just a little bit how it could have any counterpart in the supersymmetric gauge theory. Now there are various different ways of explaining that, but maybe here let me explain it using again this quivers and so basically the idea is that once you understand the quiver and then the change of the quiver corresponding to the flip, they'll be more or less done. So that's the type of the story. And now, so for example, now we want to understand it both in 4D gauge theory and the 3D gauge theory I was talking about. And in the 4D gauge theory, n equals 2 gauge theory, well, so I compactify this on R3 times S1, for example. And this has the effect that there is a nice moduli space emerging, which is a Cauchy moduli space. Well, which in some complex structure is the same as the moduli space flat SL2 connection. Well, okay, so this is supposed to be associated to some Riemann surface. So this is the Cauchy moduli space of the Riemann surface. And in fact, this is more or less a set of classical Seiberg and work of Seiberg and Witten, for example. Right, and then of course there was already a coordinate here and there on this Cauchy moduli space, which makes the symplectic form canonical. So what are the meaning of these? Well, so one way to explain that is that on this moduli space, well, first of all, there is a nice the dimension of the Teichler space is 3G minus 3G, 3G minus 3 plus H, I think. So you have G as G and the number of punctuations. So, which means that there is a canonical conjugate pair, Darboux coordinates, with the multiplicity 3g minus 3 plus h. Pairs, Darboux pair, if there is such a name, but I'm not sure. But, so there is the set of variables satisfying the canonical symmetric form. And then there is this is more like a decorated, sometimes decorated ephemeral space where you have to include the contribution from the holonomy at the puncture. So there will be h holonomies of puncture. And it turns out that it's a pair. So it's roughly speaking, there's a pi and qi, for example. Well, okay, maybe I should have used a different index from what I was using. So this runs from 1 to 3g minus 3 plus h. And there is a physics gauge theory counterpart, which is that this is a Hitchin moduli space, but it turns out this is also the same as so-called Coulomb branch moduli space. And well, it doesn't make much sense to you, but basically, if it's a U1 gauge field, there is an electron, and then there is electromagnetic duo, like a monopole, for example. And these things play the role of the electrons in the monopole. So these are related by electromagnetic duality. So in other words, these are related to gauge symmetry. So-called. Well, so it's actually more or less the same ingredient as the hyperbolic space, but I'm just changing the name to some extent. And now there's a puncture holonomy, and these are associated with Sprague symmetries. And then, well, let's see. So then, what is the meaning of the coordinate here? And the meaning of the coordinate is that, well, there was a coordinate associated with each edge of the radial triangulation. And that behaves nicely. And the meaning of that is that this Zi, so for each I, there is actually a U1 gauge field. And then you can consider the so-called holonomy. Well, okay, holonomy I'm sure you know. But it's along, so you have 4D theory compactified on S1. So you can just compactify some gauge theory on S1 and consider the holonomy. S1. And then there is actually another scalar field, and you complexify, well, which I don't explain, but there is you can complexify, for example. Everything should be complex because it's a scalar manifold. And in this type of combination, so this is a gauge field, U1 gauge field. So there's actually a counterpart to the coordinate formulated purely in gauge theory language. And then that also has the nice symplectic form as dictated by this Quiver, for example. So that's more or less a translation. Now, in the remaining 3 minutes, let me explain the connection to the 3D gauge theory. Now, the connection to 3D gauge theory works as follows. Well, so you already explained, I sort of explained the story for 4 dimensions, and we could try to translate it into 3 dimensions. And what happens is that, so the picture I have is that you have the 3D theory, which lives on the boundary of 4D. So maybe this explanation doesn't make much sense to you, but if you have a gauge symmetry here in the 4 dimensions, it looks like a Flavor symmetry here. So it's like an electric field, for example. So from the viewpoint of this guy, the dynamics here doesn't look like it. So it's frozen, so it looks like electric, external electric magnetic field. And then, right, so this quiver specifies Flavor symmetry of the theory, of 3D theory. Well, more concretely, at the level of partition functions, this means that to specify the Flavor symmetry, there is a corresponding parameter. But now also the change corresponds to grid or what else called imitations. And these are several different things, which due to lack of time I won't explain completely, but the most important part is that this should include the counterpart of quantum dialog. And the counterpart of quantum dialog is that it's a matter multiple. So there is a matter Q quantum dialog. And then, well, okay, maybe this explanation doesn't make much sense to you, but if you compute some partition function, if there is a more matter, there is a contribution. And that actually coincides with the Q dialog. So let me explain a little bit more. Oh, okay, maybe I have more than 3 minutes, sorry. Yeah, let me spend 1 minute. So what is, right, so I think you're very familiar with well, first of all, volume, for example. And you can go to quantum regime, and there is this quantum dialog, which is associated to tetrahedron. So this is the modulus. So this is what you do, but in 3D hyperbolic geometry. But now you can also go to 3D n equal 2 theory. Then you have the same combination. But what is the argument here? Well, the argument is something called, it has a real part, imaginary part. Well, in this notation, probably log exponential, right? So it's something called a flavor. First of all, the real part is called a flavor charge. And so if you have a tetrahedron glued together, there's a gluing equation that the product of z is equal to 1. Well, or z prime, etc. is equal to 1. And that's translated to the condition that the sum of the flavors charge equal to 0. And then similarly, there's angular part. It's known as something known as R charge. And then probably you don't care about the name, but the point is that the sum of the R charge is normalized to be 2. And that's just like the angle, for example. The sum of the angle is supposed to be 2 or 2 pi. And that has a counterpart. And the sum of the flavor charge is supposed to be 0 in physics, and that also has a counterpart, for example. So, so this is a small, well, I didn't explain the whole story, but the small indication that whenever there is a parameter like Q dialog, for example, with some parameters, you can translate it to different language, for example. And once you have a different language, you can construct the actual theory, 3D gauge theory, which you can, from there, you can also compute other different partition functions. And the type of the story I'm explaining here works for general 3-manifold, and sort of provides the point. My talk is to first of all the cluster algebra structure is there in the hyperbolic 3-manifold. I hope at least that part you get, and then you can try to provide various operations to the quantum dialog, taking Fourier transform. There is a gauge theory interpretation of Fourier transform, etc. So many operations, in fact, probably almost all the operations you do to the quantum dialog has the gauge theory interpretation. And by going through that, you sort of categorify or QFT-fy the rich story of hyperbolic geometry and its quantization. So let me finish here.
So as concerns that three-dimensional theory,
yes.
So on the cluster algebra, it corresponds just to surfaces, triangulated surfaces, right?
Yes.
But you say that you can, do you mean that you can interpret in three-dimensional terms more general cluster algebra?
Oh, right. So that's an interesting question. And well, I don't know the whole story, but for example, there are some cases, for example, you can realize so namely, if you just have a cluster algebra, as you say, it's just a two-dimensional surface and just one dimension. So you can do mapping torus, etc., but not general 3-manifold. However, for example, you can first try to do the mapping cylinder, for example, and then try to put appropriate boundary condition.
But all this corresponds to triangulations eventually.
Yeah, triangulation, yes.
Special particular case of cluster algebra. But let us take exceptional cluster algebra.
Okay, I see. Then I would say that I don't have a geometrical picture underlying that. So in other words, well, I don't know how to explain in a better way, but for example, there is if you consider so cluster algebra is so very general, and then if you have a three-manifold, there is a particular gluing structure of the gluing, for example, how things glue together. For example, if the I don't know, if the edges in the tetrahedron you can glue together, for example, and things like that. But if you have more general cluster algebra, for example, the general gluing becomes more general, for example. So for that reason, I don't necessarily have a geometrical picture, for example. Well, but that depends what you might want to do. But if you're interested in more, but to some extent it's interesting that because people often emphasize that there's an M5 brane compactation, that's why how this story works. But it's not just about M5 branes. Even when there is a more abstract cluster algebras, and even in those cases where there is no underlying M5 brane picture, the correspondence between this cluster algebra structure and the 3D gauge theory works, for example. And actually, I do think that has some interesting implications to the physics also. The cluster algebra is actually something more or less the so-called algebra loop operators in 3D gauge theory, for example. The algebra is spanned by two-foot loops and Wilson loops and all that. And you can use that as a defining data for 3D theory, for example, instead of Lagrangian. So, sorry, that's a physics one, maybe you don't care, but at least there is such an interesting point, I think, for physics applications too.
Sorry, we have no time to for more questions.
Sorry, yes.
Thank you very much.